So I was inspired for a long time to make sure that the universe was for everyone. Everyone could access information and knowledge about the universe.
That's Chris Harrison, and together with his colleague James Trayford, they not only want to bring the universe to everybody, but they want to do that with the help of sound. But how do you go about representing data with audio? Well, I met with both of them to find out. A lot of effort has gone into representing data through graphs, pie charts, histograms, and plots of all kinds. Over the past decades, we've developed a kind of a design language of how to represent data visually. And of course, there are lots of tools available like the famous D3 JavaScript library, to name but one. Obviously, this doesn't work for everybody. For one, there are visually impaired people, or people who are blind, who won't be able to see your fancy plots and histograms. But in addition to helping them, there's also an element of bringing more oomph to a presentation by letting data literally speak for themselves with audio. Like for instance, a few weeks ago I published an episode about the Voyager space program with my guest Bill Kurth from the University of Iowa in the US, who played back some, at times eerie, sound samples recorded by Voyager. Well, of course, you can't hear sound in space, but Bill showed how data can be represented with audio all the same. And that's exactly what my guests for this week, Chris Harrison and James Trayford, aim to do with the project they set up. A project with the appropriate title of AudioUniverse.
I'm Chris Harrison. I'm an astronomer based at Newcastle University.
Yeah, hi. I'm James Trayford. I'm also an astronomer here in Portsmouth on the south coast of the UK, interested in galaxies, but also how we can use sound to convey data.
Indeed, that's exactly what we want to talk about today, because how can we use sound to represent data? The project that you created, it's called AudioUniverse. I think it requires some explanation to the listeners what that is and what exactly it is that you're trying to achieve with that.
Yeah, so I'll tell you a little bit about AudioUniverse. So AudioUniverse is a project. At its core, we're trying to turn data into sound. And there's a few reasons we want to do that. Mm-hmm. One is to create immersive and engaging ways to communicate data. Another is to create educational resources that are fun for everyone, but are particularly accessible to those who prefer or need non-visual communication methods. And the third reason is to create a new mode of interacting or exploring data sets that might be really complicated, multidimensional, and visual methods just don't cut it when we want to get the full information content of those data.
Right, and how long has this project been running?
We sort of formally launched in 2021, so that's about 4 years now, although we did some preliminary work just before that.
And what made you actually do that? Why this project?
I can give you my motivation, and James will probably have his own. So I was inspired for a long time to make sure that the universe was for everyone. Everyone could access information and knowledge about the universe. That's always been a core value of mine. And then I had the privilege of meeting a colleague of ours, Dr. Nick Bond, back in 2019, who is a blind astronomer. And he was showing off some work he'd been doing using tactile methods to communicate astronomy to blind and low vision children. And having a bit of a background in music myself, I was like, oh, wouldn't it be wonderful if we could bring the universe to life through sound? And then I started thinking about that, and we created some projects together, and it really led from there for me.
Mm-hmm. James?
I suppose for me, it was really not like a planned thing, I suppose. My background's really in sort of the theory of how galaxies form and evolve. So I was working on these massive simulations of the cosmos, basically, to model these things. And you're left with such an abundance of data, so much data, so many dimensions of the data, that it's hard to know sometimes what to do with it. So I was working a lot on visualizing this data, for example, so we can experience it visually, as we tend to do. But it really got me thinking about like other ways we could try and communicate the data. So that's really when I started playing with sound, and really that came out of my background, like hobbying with music and sound, stuff I'm really interested in. And those things sort of came together, and then meeting up with Chris and hearing about his project and his designs on this on a larger scale, that really gave me the impetus to work more on this and to find a way to bring these things together, to express data in a new way, I suppose.
So it started in 2021. That was during the pandemic. Did that have any impact why you got together and created this project? Or is this completely independent of that?
I guess it was sort of independent of the pandemic, but it maybe gave us time to focus on different things, which was quite fun. And sitting in our computers and turning data into sound in our own little rooms was something we could do during the pandemic, and that worked really well. Yeah, I think that there was a couple of challenges as part of that, because we're working with communities of blind and low vision people and children at the time. And so we were planning to do a lot of focus group work, engaging in conversations, and that all shifted online. But, we had this way of communicating that worked. So, yeah, it was good fun.
So how many people are working on this project right now?
Yeah,
is it you two and plus? Or?
Yeah, so myself and James are leading the project from our respective locations. Yeah. We have a handful of core members. So we have a PhD student at Newcastle who's doing a lot of the research behind the sound design and the best methods to represent the data. We have a couple of software engineers too who do the coding side of it, one based at Newcastle, one based in Portsmouth. And we have a couple of primary consultants who help us on the education and the accessibility side. Beyond that, there's quite a lot of people who are involved at a lower level. So various astronomers, educators, school pupils, community groups, musicians, who've all contributed little bits along the way as well.
So you focus on astronomy because that's your background. Are there any kind of data representations in sound in other areas that you're looking at as well? Or is it specifically, as the title suggests, universe, audio universe for astronomy?
Yeah, well, we certainly started from astronomy because that's our own background. Of course, we're astrophysicists, so we're most interested in that. But recently, we have been exploring using different types of data sets. And, for example, climate science data sets we've been working with. I was communicating with some people working in ecology, and we made a fun couple of ecology examples. So we're definitely expanding out. The methods we use are agnostic to where the data came from. So data is data. And so we're really excited to reach other domains as well.
If I can summarize, so there are three areas. So there is, how do you create an immersive experience for data and how you perceive data? Then there's the educational aspect. And then there is how do you represent complex data with the help of sound? So how do you represent data then with sound? I think that's the big question, isn't it? And I guess we're getting some examples a little bit later, but how do you approach that?
So that's a really an interesting problem. So I suppose we're talking about lots of different aspects of sound that we can combine in different ways. I think we all know from listening in our world to the kind of the range of different sounds and the complexity sound can have. At the base of it, of course, sound is like a 1D time varying signal. You can represent it as a waveform. You might be used to seeing this in a digital form on your computer or something where you just can draw out a waveform. But that waveform contains a lot of information in very little time. You sample that waveform on the order of 50,000 times a second. So that waveform can contain a huge amount of information. And actually, perceptually, there's lots of different properties that we can separate out and use to convey different information. There's things like the pitch of a sound, the intensity of sound, as well as more abstracted things, perhaps like what we might call the timbre of a sound. So that related to like the harmonic content. Why does a trumpet playing the same note as a violin sound different? It's to do with the different harmonic content of that sound. And we can make use of these different properties and use that to convey data, just like a star might vary in brightness over time. So, we have these pulsating stars in astronomy. You can take those variations in brightness as a function of time and map that to some changing property of a sound over time. And if you understand that relation, or that relation is intuitive, if something is increasing in pitch, say to convey an increase in intensity or brightness, that can be a very useful way of just conveying that data in an audio form. And this tends to be referred to as a parameter mapping approach for sonification. But it's just one of many ways that people have explored for doing this kind of sonification.
Sonification, thank you for the keyword. Because in an offline discussion that we had, James, some time ago, we distinguished between sonification and audification. When we talk about representing data with sound, there is the obvious point, some people are visually impaired. So for people who aren't, it's easy to look at pie charts. Hence, we talk a lot about data visualization. But people who are visually impaired, life is very different. That I believe, and I remember, and I hope I do remember correctly, that is what we call audification. Is that correct?
Yeah, so audification, I think, we refer to that as a kind of very literal form of sonification. So I tend to think of it as sonification is the very broad thing of like how we try and convey data through sound. And audification is like a specific subtype where you're hearing the data very directly. The most direct form you can think of is something like taking a signal that you detect and just playing it through a speaker. So like an example of that would be like a Geiger counter, right? So when you're detecting radiation with a Geiger counter, you have this tube and then radiation interacts with it. It generates these voltage fluctuations and you hear those directly. Those just go straight to a speaker. So this is a very literal translation of the data. And those kind of things have been used as well. There was a prominent example with the first detection of gravitational waves. They have this massive experiment called LIGO where they're measuring essentially these fluctuations in the fabric of space, essentially. And those oscillations are obviously not the same as oscillations in the air. But we can take those variations and again, you can play them, say, through a speaker. So you're directly then hearing the character of this signal. And that's where this characteristic chirp that was played could be heard. So as these two black holes merge in together, they do a sort of whoop sound.
Is there an example that we can listen to for that black hole merging gravitational?
Yeah, exactly. So an example of this would be the first ever detection of gravitational waves. Essentially, you can play this chirp and you'll hear this quick rise in frequency as these two things spiral in together. The connection between the sound and the data is very obvious to people, and especially to a public who is not used to this way of doing things. It's not used to conveying data using sound. One of the things we're interested in is if we can sort of expand this out and see if these kind of more abstracted forms of sonification can similarly be used, because it requires a level of understanding, right? You need to know how to translate between what you're hearing and what that means in terms of these properties that are physically varying.
Which is something that you have to do with visual data representation as well very often, where you need to abstract the data and distill the essence of what you would like to show visually. But how do you approach that then in terms of sound? And could you give us a concrete example?
You picked up an important point there, and what one bit of skepticism we sometimes get is this potential subjectivity of how you decide to go from the data parameters to the sound parameters. Is that a flaw of the method that you're making a subjective choice? Well, my counter is just what you said, that often that's exactly what we're doing in visual representations too. If you're making a graph, you're saying what symbol type represents this type of data? How do I scale my axes? What color bars do I use? All of these are subjective choices that the person making the visualization are doing. So it's the same thing. You want to make those choices based on how you think you communicate best the information in the data that you want to communicate. And that's how we approach it. Now, some of it starts from just our personal feeling and choices, but a lot of what we've been doing is working collaboratively with focus groups. So we try different sound designs with members of the public, or if it's for a particular application, like for the vision impaired community, we'll work specifically with that community and test the different approaches and say, well, what do you think of this? And could you hear something in the data? And we see if they can hear the things in the data that we were kind of hoping that they would be able to draw out from listening.
I'm trying to find something that we can play, maybe.
Yeah, a nice example that we can play is from the first big project that we did, which was create a show. We created a show called AudioUniverse Tour of the Solar System. And in that show, we wanted to teach people about the stars and the planets. And the idea was it was a visual show in a planetarium setting or on YouTube. but everything in the show is represented with sound. So irrespective of level of vision, you could still get the same educational experience. So we could play a little excerpt from that.
This is the AudioUniverse tour of the solar system.
Yeah, so we've got a little sequence called the stars appearing. And what we do here is every star above the Very Large Telescope in Chile is represented with a sound. You hear the brightest stars first, the fainter stars later, and the redder stars have a higher pitch and the bluer stars, no, the other way around. The red stars have a lower pitch and the bluer stars have a higher pitch.
You said there is an artistic element because you're interested in music yourself, both of you. So what decides what kind of choice you make, let's say, in terms of instrumentation, for instance? James, you already mentioned trumpet sounds very different to a violin. At what stage then do you say, okay, we'll choose a trumpet now instead of a violin? What kind of criteria do you take in order to make that call?
This is an interesting question. Like you say, there's a bit of an art to it, or there's some sort of like competing choices that you have to think about. So, you know, of course, what we want to do is actually convey the data. So the choices we make should be clear, right? They should clearly convey, should be able to clearly hear the differences. So if you use some very complex sounds or something, then maybe that's not the clearest choice. But similarly, we can make choices that are more aesthetically pleasing or perhaps sound better to our ear. And this is not just to make it sound nice. This is also to help if you make some very harsh or distracting sounds, that's taking away from perhaps your perception of the data. So these kind of choices are important, and this is not something that's standardized in the same way that a lot of things in the way we make scientific plots are standardized, right? Is that there's kind of these conventions that have emerged over hundreds of years of how you plot data. And also, you know, people learn these from school. So everyone has a kind of unspoken understanding or spoken understanding of how scientific plots work. Whereas in sonification, we're more kind of like trying different things and trying to find the best way of doing it by kind of iterating, testing with people. But one interesting avenue, I think, as well, is this idea from design called skeuomorphism. So that's a complex word, but it basically means using things that are intuitive to us, that we experience, to represent like phenomenon. So an example of this, right, might be on your computer when you drag something into the recycle bin, it makes like a scrunched up paper sound or something like that. Right, that's like an audio indicator of like a file being thrown away or something. And there's similar things that we can do in astronomy, especially to try and convey the types of phenomenon. So, for example, like stars like our sun and bigger stars can give off these kind of strong stellar winds. They're blowing out this intense, ejecting this gas in this intense way. And we can use the sound of wind that we experience on Earth, like the movement of gas around us, which has this windy sound. We can map that to something like a stellar wind. That then makes a kind of intuitive sense. It's also a sort of shorthand for the sort of type of thing that's happening. And similarly, we can choose things like a fiery sound to communicate the intensity of the burning inferno inside a star or something. This crackling, fiery sound, that's what a fire sounds like on Earth that we might be familiar with. So if we can make use of those effects, then it sometimes perhaps is like a helpful shorthand to try and get across some of what we're actually trying to get across.
Chris, you shared some YouTube channels. Is there one which highlights the wind and the fire?
Yeah, one of the examples that we've shared has actually different sound design approaches to representing these fluctuating stars. They're sort of blowing off these winds and things like this. So within that example, one of the choices we experimented with was this sort of windy sound. You can kind of experience the stars getting more powerful and less powerful.
Okay, so thanks very much for that example. The question that I now have is, how do you actually represent it in a meeting? For instance, in scientific presentation, I think you went to an astronomy meeting in July, didn't you?
Yeah, so last week, myself and James and Rose and Nick, who are all from AudioUniverse, were at the National Astronomical Meeting, which is an annual meeting where astronomers from across the UK get together. We discuss lots of topics, scientific topics, of course, but we also discuss wider topics such as education in astronomy, inclusion in astronomy. And we had Rose was talking in a session there specifically about bringing together the arts and the sciences. And of course, data sonification does kind of think about bringing together the arts and the sciences. And during that presentation, she shared some of our examples. Just like you could put up a figure, we play a sound through the presentation. And I think really it gets a much more engaging and exciting response from the audience, because you're not just looking at the data, you're kind of experiencing the data in a more immersive way.
When you do it for educational purposes, I can imagine that, if people go to, say, a planetarium and they see presentation on the planetary system, the solar system, that you get some sound usually worked in. It's been a long time since I've witnessed one. But as far as I remember, there was a music playing, etc. And that's where I can imagine sound works very well with a presentation. But in a scientific meeting, let's say at a conference where people present their results, things get a little bit more sober and down to the hard facts and what have you. Are you experimenting with sound there too? Let's say that you present a graph and then in addition to that you play something like representing wind. And how does that work?
Well, we could liven up scientific conferences a bit more, I think, and this is one way of doing that.
Yes, we can.
It can be quite dry sometimes. So most of what we've shared so far has been more tailored to a public audience and engaging maybe members of the public, but we're also working on sonification for a scientific audience. And we have another example we shared with you where we've taken a data cube, which is a 3-dimensional data set. So you have the normal kind of image dimensions, like up and down, left and right. But in the third dimension, we have this light spectrum. So every single pixel has a light spectrum. And the approach we've taken there is definitely for a scientific audience. We've taken that third dimension and we've directly transformed a light spectrum into a sound spectrum. So you've got all of that information encoded in the sound. And one thing you can hear in that example is how the gas is moving inside that galaxy. If you listen to it, you can't see the visual over the podcast, of course, but the video has somebody exploring the data cube. So they're moving their cursor around the data cube, exploring the left, the right, the center. And you can hear pitch shifts in the sound. And that tells you how the galaxy is rotating. So if the galaxy is moving away from you, you hear a lower pitch. And if it's moving towards you, you hear a higher pitch. And the other thing that changes is the characteristic of the sound. And as the sound sounds more windy, the gas is more chaotic. And in the central region of this example, the gas is very chaotic because there's a black hole releasing a lot of energy and churning up that gas. So we can quickly present to the audience, oh, this is how the galaxy is rotating. This is where the gas is more windy through a single video or sound, rather than having to show many pictures and figures, maybe a bit more boring way to also share the same information.
I'm trying to play that now. Well, thank you very much for these samples. That sounds very exciting. I would like to focus a little bit for the rest of the time how the organization as a whole, AudioUniverse, works, because you're still astronomers. How then can you keep the lights on with AudioUniverse?
Like I said, we're not a formal organization. We're more of an informal group of people who are like-minded. But it's a good question. How do you keep the things running? And we are both holding grants that are funded from the UK government. I hold a grant that's mostly focused on the public engagement and accessibility side. And James holds a grant that's more focused on the code development side. So we're developing this open source code for all of this work. So that allows us to hire team members to do some of these activities. The other side that's important is the fact that we're trying to have a direct impact in the UK and beyond with our work. So astronomy in itself is very interesting, of course, and we all love asking questions about the universe, but it's important for us to justify what are we doing if we're funded by the public to benefit society. And so these activities that we're doing really have a focus on benefiting and wider benefit, which means it is encouraged and supported by the university, the fact that we're doing these activities as well.
It's the software side that I would like to move on next. You mentioned there's open source software associated, but could you take us a little bit through the software aspect of AudioUniverse and what that entails, James?
Basically, when we started the project, we had these broad ideas of what we wanted, to represent, maybe we have a collection of instruments that represent the planets, or you hear these kind of struck notes that represent stars, and, you've got thousands of stars. So you want to be able to map all of these individual stars to the right pitch and the right instrument and the right volume. And to begin with, a lot of this was based on scripts that I'm kind of from this technical coding background and a bit of the sound design side particularly. So I was very interested in that. And I was just writing these generic scripts. And I came to realize that, the tool set to do this kind of thing didn't really exist in the form that we wanted. So a lot of those, what were like early scripts, then developed as the seed to develop this code library called Strauss, which now is a fully fledged free and open source software that you can download. It's on GitHub, and you can just use it as any other Python library. And the idea, I suppose, is that people can just integrate this into whatever they do with data, just like they might download a plotting library and use that to create plots as part of their workflow. They could generate sound representations as well. So like a lot of what we've done with Strauss is really to try and facilitate this sonification as best as possible. Yeah, in that respect, we've made this, it's kind of like object oriented, and we've got this conceptual structure where you break a sonification down into these different elements. Like you choose what the sources are. So this is like the different aspects of the data that you want to sonify. Those might be stars or planets in astronomy. It could be the stock market, or it could be like lightning strikes from meteorological data, whatever you like. And we can use that and say every time you hear a lightning strike or a star forms, you hear, say, a chime, and maybe that chime, the pitch of that chime is mapped to, say, the intensity or the color of that star, for example. This code allows you to sort of handle this mappings and plug the data in and just generate a sound out. And this is basically the idea behind this Strauss code that we're developing. And, we're kind of constantly looking at ways of improving the usability of it, particularly through sort of active examples. So, we package along with it lots of these Python notebooks that allow people to just play with data. Maybe you've never come across even the idea of sonification. You can just run these notebooks. You kind of see some graphs, you hear some sounds, and you're like, that's interesting. What if I change this parameter or that parameter? A way that people can get into it quite quickly. And, through this means, we're trying to make something that's quite a low barrier to entry, but also potentially with a high ceiling. People can make very complex, sophisticated sonifications with Strauss. And by facilitating both ends of that, hopefully we can crowdsource, we can encourage the community to start experimenting more with these sonifications and really get it to catch in our field. We think that that's the best way to realize a lot of these benefits, like accessibility. If everyone's doing sonification, suddenly the field is a lot more accessible to people who don't access visual means. Or maybe there's a lot more different perspectives on data that we're now getting through sound that we didn't have before.
So the script itself, you mentioned that earlier, and I'd like to confirm that it's Python then that you're using.
Yeah. So Strauss is written in pure Python. And you essentially can write a script with Strauss, set up a sonification and just press go, and you can generate sound that can either play back in a browser or save an audio file, along with things like audio captions. You can add a description that's embedded in audio, just to kind of make this as simple as possible for people.
And the sound samples, I guess that there is a library of sound samples that you can build on. Where does that come from? Is that something you generate yourself, or is that something that you pick from somewhere else? And how does that work?
Yeah, that's a good question. So we have a couple of different ways of doing it. One is through direct synthesis. So you can just, like a sort of an old school synthesizer where you have these different oscillators, you can press a key and that can generate, say, a sine wave or a sawtooth wave or a square wave. And we can use that kind of approach to generate these synthetic sounds and manipulate them. So, maybe we want to apply filters to that sound to change the tone of it, or we want to change the pitch and all these kind of things. We can do all that. We can generate that directly in the code. But also we have a sampler module where you might want to use sounds that are more organic, right? So maybe a recording of like a tubular bell or a glockenspiel or a trumpet or something like that. So to do this, we basically have this sampler module that can read in those files and manipulate them how you want. And we've made this so that it can plug into pre-existing sample pack files from the musical world, for example. So one thing that it supports is these sound font files. There's reams and reams of these kinds of files that you can find online and download for free. So, you can download, say, a steel drum or a steel pan, and then you can use that to generate this kind of stars appearing sonification where you hear these different notes being played using the steel drum.
All right. So what's the future then of AudioUniverse, and how do you see that going forward?
Yeah, well, I think there's sort of two main elements to this. I'll take one and James can take another. For me, my focus has been leading on the education accessibility side. And one thing that we discovered during our early work was, although we'd focused on blind and low vision children, we discovered wider benefits for children with wider special educational needs and disabilities. And that was discovered from classes coming into the planetarium, us doing some workshops in the classroom, and the teachers saying some of our SEN children were much more engaged and active and participating than normal. And we believe it was because of the multisensory nature of the learning. So we're now really building on that, and we're working on our projects at the moment with that in mind. So we've got additional focus group works, a specialist consultant on broader special educational needs, and seeing if embedding sonification into the educational process will have a wider benefit beyond the obvious beneficiary, which is the blind and vision impaired.
James?
I think from my perspective, one of the things we want to do is really facilitate people doing sonification. So we developed this tool and we're using it to make lots of different examples, but we really want to encourage the community to use it and use it for different data. All these different researchers know their data very well. They know when their data is coming across or when it isn't. They might have good ideas of what sort of features that they want to bring out of the data to communicate it. So really giving scientists the tool to be able to express their data in this different way through sound is something that we want to try and build as much as possible. So really, so that we can really crowdsource sonification and we can get it in these different places that lots of people use. So one example of this is we built sonification functionality into this interface for the JWST telescope data. So people can listen to these data cubes from this telescope. And this is like a resource that many, many astronomers will be using to try and understand their data. So having sonification examples in there that people can use, that people can start to grow an understanding of, will hopefully lead to this increasing sort of literacy in sonification and this increasing skill set, so that you can try and catch up with these visual approaches that we're so used to relying on.
So you've been doing this now for 4 years. So what's the response been like? So how do people actually take on board your vision of, your audio vision? It's kind of a weird expression, but your vision of representing data with sound.
I would say that on the positive side, we get a lot of really good response. People are really excited. We present this in various different contexts, education, research contexts. I want to do this. I want to take my data and I want to turn it into sound, because I think people really see the added value from a teaching side, from a communication side, from an accessibility side. So we've really got a hook, I think, that people are engaging with. The challenge, which is what James has just been discussing, is how do we go from that hook to making it so people can make it themselves and really get on and make their own sonifications. And I think there's a big barrier there that we're still working on. because of the lack of literacy and knowledge in this process, it's completely new. People are already very busy working in their own methodology, and to decide, I'm going to learn a whole new process, a whole new way of communicating my data is quite a big ask. And so I think that's the challenge that we need to facilitate and overcome. How do we make it easier for people to get started? And then hopefully you get a few adopters and then it grows from there.
What's your plan in terms of when your grant ends? Do you have any ideas of how you want to move that forward afterwards?
Yeah, that's always the question. What do we do?
It's the $1 million question, isn't it?
Yeah, well, $1 million would be just fine, actually. We could do a lot with that. Some of it is trying to build in sustainability. So that's this building tools so people can continue without us, and one of the projects that I'm working on is to make a toolkit for planetariums so they can continue to make the sonifications without us needing to be involved. That's one of the kind of legacy sides of it. The other is continuing looking for new funding to keep building and growing. I think there's a lot more work that we can do in the software side, particularly to make it easier for people to use, to disseminate it. So we're always keeping our eyes out for new funding opportunities.
Well, I hope people will get in touch with you about that. James?
Just exactly what Chris said, and also, like I say, looking at these different opportunities, because what we're talking about is quite a fundamental or broad thing. Like we'd said before, it's not just astronomy where this is useful. We're also open to sort of looking beyond what would tend to be narrow streams of where you might look for funding or support. But with a code, Strauss, for example, one interesting avenue that we've been looking at is there's bodies like this Software Sustainability Institute that's interested in making code sustainable in the long term, supporting, its maintenance. And things like this would be very useful for a project like us. I think this kind of institutional support is really important because it also grants, again, more of the legitimacy to what we're doing. So just on the individual level, we find people who are very excited. When you've actually got institutions saying we're supporting sonification, or in our journal, we're going to allow you to play audio examples as well as figures or something like this. That kind of institutional support is crucial to really realize a lot of the benefits that we're striving for.
Okay. Well, thank you so much for your time today. That was great. And I think it's very exciting. I had an interview recently with somebody from NASA who actually did sonification plasma waves, Voyager. And I think that fits in very nicely. It's also astronomical data. Now, that was fascinating, and I wish you all the best for the future. Thanks for your time.
Thanks, Peter.
Thank you, Peter.
As per usual, you'll find the links to the AudioUniverse project and the link for the GitHub repository of the Python code for Strauss, the software they use, in the show notes. Next week, we'll go to sunny Southampton at the south coast of the United Kingdom and have a chat with James Baker. James is heading the digital humanities there, and I went down from London to meet him because they do a lot of exciting stuff there. So I hope you tune in then. Oh, time's up. See you next time. But before I forget, this podcast is covered by the Creative Commons license. See ya.